CDF for -2 to 1. You draw a picture. Brendan, what do you think?
Isn't it represented the amount of, like, how much the data falls in between the second deviation to the left and the first deviation to the right?
So if you're 2 standard deviations below the mean
And
and 1 to the right of the mean, so these are our z-scores, right?
isn't it representing the data that falls in between them?
It's the area under the curve, guys, which represents the percent of data that are between 2 standard deviations below and 1 standard deviation above the mean. So if we think of our, from -2 to 2, that's going to be 95%, right? So if we take half of that from the mean to -2, that would be 47.5%, right? So 47.5% is from the mean to 2 standard deviations below. And then remember, within -1 to 1, that's 68% roughly. So from the mean to 1 would be half of that, which would be 32%. So if you take 32% plus 47.5%, you get, was it 79.5%? And if you type that in the calculator, so you go to your distributions, second variables, in the distributions, do the normal CDF, -2, 1. There's maybe some wrong in there. Did I do that right?
I got closer to that one number when I did it.
This number?
I added 68 plus 13.5.
68.
Because I did
Oh.
the 2 middle ones, and then from -2 to 2 is the 95. So I did 95 minus 68, and then divided 27 by 2.
Oh, okay, so you did this. So you took 95% is between, right?
Yeah, I
From
did
-2 to 2, and then you subtracted
68 from that.
68 from that.
And then I got 27, then I took 68 plus 13.5.
Okay. Why this doesn't- Well, anyway, you get the ideas with this.
68 divided by 2 is 34.9.
Oh, that's where I made a mistake. Thank you. So this is 34%. So then if I add those, I get 81.5%, right? Yes. Okay? So normal CDF, what that does is it goes from z-scores, so a range of z-scores, to the percent. That's what normal CDF does. So inverse normal is going to go backwards. It's going to go from a percent, and it's going to tell you the area below that point. So the inverse norm of 0.82 is going to tell us where is the z-score where 82% of the data is below it. So if 82% is below it, then 18% is above it? Is that right? I think I did my math wrong, because that doesn't work out to be a whole number z-score, does it?
It's like 0.9.
Yeah, I think I meant for this to say, what was half of 30, I must have done the same thing here. 68, 32, I think I meant for this to be 16, so this should have been 0.84. So if this was 16%, if we leave 16% in each tail, that'd be 68% between, so this would be a z-score of 1. That's what I meant. Must have forgot my rules there, or did some silly mental math. Okay, so inverse normal tells us what's the z-score that gives us that area below it. All right? So let's go back to our class examples. We did 5A yesterday and 5B. So we were talking about the fuel economy of cars. So if we look at the 99.7 rule for Part A, fair enough to say almost all cars get between 6 and 42 miles a gallon. That's assuming the fuel economy of cars is normally distributed. Maybe it's not, I don't know. One thing we could do to check this assumption is we could get a data set of a bunch of randomly selected cars, look at their fuel economy, and make a histogram. The histogram should be roughly unimodal and symmetric. Here we have a histogram of weights of people, and we see that it's right skewed. So that indicates that the normal model is not appropriate. You can also make what's called a normal probability plot on the calculator, and that's what this is. It kind of looks like a scatter plot. What you're looking for in there is a linear normal probability plot. And we can see that we have a curve in this, so that would again tell us that it's not appropriate. So let's pretend it would be appropriate for fuel economy of cars. If we made a histogram, they'd be unimodal symmetric, the normal probability plot would be linear. So then what we did to answer part B, what percent of all cars get less than 15? We made a sketch of our normal model. We put 15 where that would be. It'd be somewhere below the mean. We find the z-score, and then to find the percent, and this is the notation I want you to start getting used to. The p, the percent, it's actually a probability of getting a z-score in the normal model that's less than negative 1.5. Because that z-score is 1.5 standard deviations below. Okay? And when we did that normal CDF, we get about 6.7%. So what we're going to be doing to find our answers is, if we're given a value like we were in this case, we're going to convert it to a z-score and then find the percent using the normal probability CDF, normal CDF. In other problems, we're going to work backwards. We're going to be given a percent. We use inverse normal to find the z-score, and then we do some algebra to find the value. But in both cases, the middleman here is the z-score. We have to revert back to that z-score formula, which is right here. It's the y minus y bar over the standard deviation. Okay? So let's take a look at part C. Any questions on A or B? And basically, when we convert to a z-score, we're converting it to the standard normal model, whose center is at 0, and these values here are just counting the number of standard deviations away. And that's where the 68, 95, 99.7 rule apply, and all the other values that are stored in our calculator are on that table. All right? So now let's do part C. When you see these types of problems, guys, think of the think, show, tell that the book kind of models these problems after. And make sure you don't get lazy and actually do all the steps on your paper. It's going to help you out. So in the think stage, what you should do is just draw a sketch of a normal model and talk about what we're looking for. So we've got our mean at 24 miles per gallon. Doesn't have to be an elaborate sketch. We're wondering what percent of cars get between 20 and 30. So 20 is somewhere below the mean, and 30 is somewhere above the mean. Agreed? I wasn't precise in where I put the 20 and the 24. Okay? But what I'm looking for can then be shaded. So that helps me think about what I need to find. So I'm given two values. So I have to convert values to a z-score to figure out the percent. Okay? So what I need to do is change these to z-scores. So I'm going to take 20 minus 24 over, what was the standard deviation? 6. And then this one I'm going to do 30 minus 24 over 6. So here I get a z-score of negative 4, 6, which is equal to negative 2/3 reduced. And over here I get 6 over 6, which is equal to 1. I've just converted those to z-scores. So essentially I'm saying 20 miles a gallon is 2/3 of a standard deviation below the mean. And 30 miles a gallon is 1 whole standard deviation above the mean. So what percent of cars are in there? So what we're looking for is this percent, P. And to find that percent, it's equal to the probability of getting a z-score that is between those two z-scores we got. So this is part of the show. You're showing your work with the z-scores, and you're showing what the p-value means in terms of that. So the percent is the probability, that's this p, of getting a z-score between negative 2/3 and positive 1. Now the next part, you don't really, like on the AP exam, they want to see this. You can put this next part down just to help you remember the calculator commands, but it's not required. So we found the values, we converted to z-scores, now we use the normal CDF to convert to percents. So now this time, it's just the normal CDF from negative 2/3 to 1. You put the low number first, comma, the higher number. So on here, I go to second variables, normal CDF, negative 2 divided 3, upper is 1. Or if yours doesn't work like this, it's just negative 2/3, comma 1. You don't need to put the 0, 1 afterwards. I think if you do, it'll still work. Yep.
You're saying that, like that's, like the probability part is that's like what we're doing, but the normal CDF is what actually does it on your calculator?
The normal CDF is just the button, the command the calculator uses to answer that question. Yep. So our answer is about 58.9%, 0.5889. And it's I approximated there. So then there's your show, think was the picture, show was the work, and then the tell. So the tell is to put your answer as a complete sentence. So 58.9% of cars get between 20 and 30 miles per gallon, according to the normal model. I say that because, I mean, it's not a bad habit to get into. That isn't guaranteed, right? There's a saying, all models are wrong, but some are useful. Okay? It's probably not exactly 58.9%. But that's what this normal model that we've used to represent the distribution of fuel economies of cars tells us it'll be. So it's probably, hopefully pretty close if this model is an accurate model. I call these wiggle phrases just to say, you know, there aren't certainties in a lot of what we do. So think the picture, show the work, tell the complete sentence. Questions on C? All right, now D. See if you can do that one yourself. Think, draw a picture, show, write out your work, tell, complete answer.